Hello everyone. Today we will be covering 5 actuators. First one will be solenoid. So let's start with the discussion of solenoid. For instance, this is your winding and this is your armature which moves back and forth. So we have windings. So these coils are like this, goes from here all the way around. And this moves back and forth. As per the right hand rule, if you have a wire, then there is a magnetic field associated with it. But in the case of solenoids, because these coils are winded around the armature and they are something like this, and when we pass current through this, we get a magnetic field with polarity of north and south. And actually this is opposite of what it is inside. For instance, if we have north-south here inside the coil, then outside of the coil it will be south-north. But for now we are just concerned about the magnetic field inside the coil. Since a solenoid is able to produce two poles, so when we run a current through it, or when we pass a current through it, we have a poles induced, and this is soft iron. Which is a ferromagnet. And the property of ferromagnet is that when it comes in the contact of a magnetic field, it induces opposite poles. So if you have a north-south in the coil, then you have opposite poles induced in the core. Now what will happen, there will be a center of the magnetic field of the coil, and there will be a center of magnetic field of the armature. And we can clearly see from this figure that the centers are not aligned. And in this situation what happens is, the center of the magnetic field of this will try to align with the center of the coil, and this whole armature is being pushed towards this side. So this is the basic operation how a solenoid works, and this is just a linear actuators. Whenever we need to open and close the valves or similar kind of operation, we can use linear actuator, and it's very common in the industrial purposes. So let's move on to the next actuator. So the next actuator will be the amplifier. We are using two kinds of motors, brushed DC motor and brushless DC motors. So before going to the theory of, before going to the actuators, let's consider a little bit of theory regarding the amplifiers. So there are two kinds of amplifiers. First one is a linear amplifier and another one is a PWM amplifier. But before going to the theory of amplifier, I would like to discuss a little bit about the duty cycle. We previously saw how a linear actuator works, but now since I have a 24 volt signal and I don't want to provide a 24 volt signal to the linear actuator. For instance, I need just to provide a 12 volt signal, 6 volt signal, 3 volt signal, because my linear actuator is not capable of holding that much of voltage. So how do I reduce the voltage? Because I just have 24 volts available to me. So in that case, we use a duty cycle. So here is my signal, 24 volts with respect to the time. If we see a DC signal, it will appear like this. With respect to time, there is almost no change. Let's consider the signal in the time domain and break. So I am plotting it with respect to the time. Now, what if I want a duty cycle of 50%? So I will turn off this here, and then when first it reaches the first pulse, I just turn it off. So this is a high signal, and then this is a low signal. Here it is off. After that, it again goes to high, and the signal is repeated because we are just running it at 50% duty cycle. So it is just a cycle of on off, on off, on off, because we have a 50% duty cycle. And if we look over the resulting signal, it will look like this. So instead of having a continuous signal, this was a signal that was available to us before applying the duty cycle on it. Now our resulting signal is not continuous, it is not a pure DC signal, and if you average out the signal, so the overall value will be lesser than what we had. And so if you are going for 50% duty cycle, it will be around 12 volts. Now let's consider 75 or 25% duty. So in that case, I have 3 on cycles and 1 off cycle. No, we are going for 25%, so 1 on and 3 off. So resulting signal will be like this. Let me erase the unnecessary parts. So this is the shape of the resulting signal, and our output will be around 6 volts. So what will be the formula of duty cycle from this discussion? We can see that duty cycle is basically on time divided by on plus off time. So that's on time divided by the total time. So we use a similar concept to amplify the signals. Maybe we need to increase or decrease the voltage, and we use a similar concept of duty cycles, and the signals generated are known as PWM signal because we are modulating the pulse of the signals. So PWM stands for pulse width modulation. Here you modulate the pulse width to change the output voltage. So if we compare those two signals, they will have a different output voltage because of their different pulse width. So this phenomena is known as pulse width modulation. And the voltage output is proportional to the duty cycle. Second method of the amplification is a linear amplifier. That's the most basic method in which we use op-amp. So for the purpose of our experimentation, we will be using a non-inverting op-amp, and I will draw its diagram really quick. So this is resistors R1 and R2. And this is grounded. And this is our output. So the reason why it is known as non-inverting op-amp or non-inverting amplifier is that we provide the electrical signal through the positive terminal of the op-amp. If we provide the electrical signal through the negative terminal, then it's known as inverting op-amp. So we are not going over the theory of op-amps because that is beyond the scope of this class, and I expect the students have already learned the concepts in their electrical classes. So what I would cover is, if the amplification ratio, that is equals to V out over V in, sorry, so when amplification ratio of the op-amp tends to infinity, our output signal, that's V out over V in, is driven by the combinations of the resistors we use or we choose. So it is basically 1 plus R2 over R1. Now if we need for instance, if we have a 24 volt signal as V in, and we need some other voltage to run our appliances, so we can just go here we can change the combinations of our resistors to get any kind of voltage we want. So we can amplify it, we can reduce the signal without modulating the pulse. So this is a non-PWM method of amplifying the signals. This is comparatively expensive as if we compare it to the PWM signals, because PWM can be generated by just modulating the pulse. However, you need a specific hardware op-amps for this purposes, and that relatively increases the cost of the equipment. So here we covered two methods of the amplification. Now we will go over the actuators after this. So the next concept that I will be covering is HBridge. Suppose we have a motor. Now we know how can we go from 12 volt to 6 volt, 3 volt, 1 volt, or whatever we want. But if we want to have an actuation in opposite direction, or in other words, if we want to rotate the motor in other direction, what are we going to use? What are we going to do? So for that purposes, we use HBridge. So we have 4 switches in this case. And these switches are basically the MOSFET transistors. And here is my motor. 1, 2, 3, 4. And here I provide the positive signal, and this is my ground. This is my motor. So this is the HBridge. If I sort 1 and 4 terminals, so if I sort this terminal and this terminal, so what is going to happen? I would have a current flowing in this direction, it will go to ground. So 1 and 4 leads to this direction. Let's and the other direction. Now if instead of having the current flowing in this direction, I want the current flowing in another direction. So what I will do is I will sort 2 and 3 number switches. I'll go ahead and do it. So current will start flowing from this direction. It will go like this, and then through this it will go to the ground. So by using the HBridge, I can have a rotation in positive as well as negative direction. So it covers the entire range. We can have a rotation in dual direction. Now the next concept is the deadband. So deadband is basically a delay in the operation. So in our experimental purposes, for the setup we are using, when we provide a certain amount of current to the motor, it does not start moving. And there are certain reasons for that. There is a magnetic friction, or because our motor is like this. So these are the various magnets for it. Let's consider this is a stator and this is a rotor. So it has some poles, So those poles are already aligned to each other. And when we provide a very little amount of current, it is not able to overcome the forces that magnetic field is providing. Or the second reason is there is a static friction involved in this process, and until or unless the static friction is overcome, the motor is not going to rotate. So let's consider we started from 0 volts and we kept on increasing the voltage, and for instance it started rotating at 2 volts. So here we can see that there is no rotation from 0 volt to 2 volts. So this particular region is known as deadband. And also we can see in the negative direction, so this is the positive deadband, and we will also have a negative deadband. So going from 0 volt to some XYZ value, it could not be -2, it could be something else, but we will have a deadband. That's a region in which there will be no rotation. So we can write it like this. So for our experimental purposes, we are interested in finding out the region in which the motor does not rotate, and that will be regarded as a deadband. Now we will go over the fundamentals of how a DC motor works. For this we use climbing left-hand rule extensively. Suppose this is our stator, and this is a rotor. So because of these permanent magnets, we will have a magnetic field associated with it. So that will be B. And we are passing the current. These are the carbon brushes. And these are known as commutator ring. So let's consider if we are providing a positive current from this side. So the direction of I will be like this, and B is in that direction. So Fleming left-hand rule says F is given by I cross B. So I cross B is going down inside the plane, or I should draw it like this to be more clear. And if we come to this side, B is in the same direction. However, I is in the downward direction because I is flowing like this in a closed circuit. So now in this case, F will be given by I cross B. It's coming out of the plane of the paper, and this is going inside the plane of the paper. And if this is our rotor, then this will try to rotate like this. Now after half rotation, this will go there and this will come here, and our diagram will look like this. So actually what happens is, now since you had a current going through this arm, right, and it flows back here, now this has twisted, so this goes there, this comes here, so I is pointing down, so we will have a I like this. However, B is same, and the resulting F will be coming out of the plane of the paper, something like this. And now if we use the same concept by similarity, we will have a rotation like this in the opposite direction. So our motor will try to rotate one turn clockwise, one turn anti-clockwise, one turn clockwise, one turn anti-clockwise. And to avoid that, we use commutator and rings and the carbon brushes. So when rotor rotates, this commutator rings loses connection with the carbon brushes, and this detaches from the carbon ring, carbon brush, and attaches with the carbon brush on the other side. And due to that, we still have I going up and F going in this side. And this clearly implies that the rotation will again be like this, and we have a continuous rotation in this case. instead of having zigzag motion, we have a continuous rotation. So that's what the basic fundamentals of working of the motor. Now if we move on to the brushless motor. Now if we don't have brushes, what are we going to do? So in the brushless motors, for instance, this is my stator and this is my rotor. So instead of having a permanent magnet in the stator, this is our stator and this is obviously rotor. So instead of having permanent magnet in the stator, we have a permanent magnet in the stator rotor, and these magnets are the temporary magnets. They are like solenoids. So we can name them A plus minus, B plus minus, and C plus minus. So when we turn on A, there will be a magnetic field induced, and this magnet will try to align with the magnetic field of the coil A. And when we turn on the magnet B,